I'm Anil Kumar. Welcome to my series on quadratic relations for grade 10 students. In this video, we'll discuss the topics mentioned here. We'll also take up many test questions as we move along and understand the basic concepts. To begin with, let's try to understand what are quadratic relations and how to recognize them. So, a couple of ways. One, from the graph. So if I sketch a graph, then on a graph you could recognize quadratic relation by a curve which looks like a parabola, kind of like this. So any curve which is U-shaped as shown here, it can open up or it can open downwards. That type of a shape represents a quadratic function, right? We could also find whether the given function is quadratic or not if we have the form of equation as y equals to ax squared plus bx plus c, where a is not equal to 0. This is important, correct? So I hope that makes sense. If a equals to 0, what you get is y equals to bx plus c, right? This is linear. Perfect. So a should not be equal to 0 in the given equation ax squared plus bx plus c to make it quadratic. Correct. So these are two basic things, and of course, whenever we sketch a graph, we take x on the horizontal axis, y on the vertical axis. So at times I may not be writing x and y or the origin. We'll just sketch the graph, correct? Linear functions, you already know, will represent by a line, right? It could be going upwards or downwards, or could be even horizontal. So what we see here is nonlinear includes quadratic functions which are kind of a parabola. Now there could be other nonlinear graphs. Whose shape could be not like a U shape but kind of like this. Do you see that? Or maybe something like this. These are other graphs which are not representing quadratic functions. So I hope that part is clear. So quadratic functions will be represented by a graph of this kind, that kind, or by an equation which is y equals to ax squared plus bx plus c, where a is not equal to 0. b or c could be 0. So I hope that point is absolutely clear. So now let's move on and test some equations, whether they are quadratic or not. We have two equations here. You need to determine whether each function is linear or quadratic. So the idea is to simplify these equations. Looking at them, you could say, but at times you could be wrong. So we'll just see how. So the first one, let's apply the distributive property. So we'll first multiply by x both the terms and then by minus 1, collect like terms and then simplify. So what we get here is 2x squared plus x, with minus we get minus 2x minus 1. Combining the like terms, we get y equals to 2x squared minus x minus 1. Now here you see that we have this x squared terms, so it is quadratic. Correct? And a is not equal to 0. So that is a quadratic relation. Let's look into the second example. So let's again expand. So what do we get? We get y equals to 2x squared minus 4x minus 2x squared plus 4. Combine the like terms. Now let me rewrite them. We have 2x squared minus 2x squared we have minus 4x plus 4. So 2x square minus 2x square is 0. What you are left with is minus 4x plus 4. Clearly, this is linear, right? Now, if you look at it, we do have a x square term. However, it cancels out. So it is not a quadratic function. It represents a linear relation, okay? So this one is a linear relation. So be careful when you answer such questions. They may look obvious or simple, but you may get them wrong in tests. These are actual test questions, correct? Now let's look into finite difference and then try to figure out whether the data represents quadratic function or not. Now we'll do the test which is called finite difference test to check whether the given relation is linear, quadratic, or neither. Now the function is linear if the first difference is constant, quadratic if the second difference is constant, and neither if first and second are not constant, correct? Important thing is that quadratic function's second difference is constant and not 0. This is important, right? Okay. Now, what do we mean and how do we find the difference? Let's look into that process. So here we are given x and y values. When I say first difference, what we really need to do is to find y2 minus y1 for the change in x. Okay, so that is what we have to do. Now, whenever you find finite difference, check for x value. So first thing is you need to check that there is a constant difference for all x values. That is very important to check. Then you start finding, okay? Otherwise, the data may give you wrong results. What I'm trying to say here is, if you check this x values, they are moving up by how much? +1 each time, right? So +1 each time, which is constant. Correct? Now, let us find the first difference. So this check has been passed. Now, what is first difference? First difference basically is we need to find change in y value. That means we'll do this minus this. So we are trying to do -3 minus 0. So we get here -3. Then again, we do -4 minus of -3. You get the idea, right? This is what you have to do. So -4 plus 3, which is -1, and then you do -5 minus of -4, which is -5 plus 4, a value of -1, and then what you do is 0 minus 5 minus 5, which gives you +5. So clearly, first difference is not equal to a constant. It changes, right? So now let's go for the second finite difference. So we'll write that as delta y2. So this represents my second finite difference. Okay, so here we have -1 minus 3, right? So when you do -1 minus 3, what do you get? So we get -1 minus of -3, which is equal to 2. Now here we have -1 minus 1. So we have -1 minus of -1, and that gives you 0. And in this case, we have 5 minus 1, 5 minus -1, that gives you 6. We find that the second difference is also not constant. So therefore, in this particular case, it is neither, correct? So in this case, it is neither. So let me write down. So we have a function which is neither quadratic nor linear. So here we get the answer as, let me write down, neither. Okay. Now let's look into the second example. In the second example, you will notice that the x values are actually changing by how much? They are changing by +3, but still it is constant, right? So that means you could actually find the first and second difference, correct? So let's find first and second difference. So again, we made a check. This is true. We have a constant finite difference. And now 3 minus 2 is 1, 6 minus 3 is 3, 11 minus 3 is 5, 18 minus 11 is 7. So we got the first difference, which is not constant. So now let us find the second difference. So 3 minus 1 gives us 2, 5 minus 3 also gives us 2, 7 minus 5 is also 2. So which is constant? 2, and therefore we can say that this particular data represents a quadratic function, right? So this represents a quadratic function. Since the second difference is constant, it is equal to 2. So I hope you have understood this process. What do we mean by second difference being constant? Correct? Now here is a true or false question for you, which is, if the second finite difference is constant, then the data represents a quadratic relation. True or false? What do you say? Well, this statement is false. You know why? We have to also mention that it has to be non-zero. This is important to say. Non-zero. So if the second finite difference is 0, which is also a constant, in that case it is a linear relation, not quadratic. So at times these types of questions could be very tricky, so be careful about it. So let's move on and now understand what is a parabola. Now let's try to understand some typical features of a quadratic graph which looks like a parabola. So let me sketch here one and then we will kind of label it. So normally we could have some structure which is like this. Now I've sketched a graph of a polynomial function y equals to x square. Now you could actually make a table of values to sketch it. So what I'm trying to say here is that you could write some values of x, calculate y. Good values to take are -2, -1, 0, 1 and 2, and square them, you get positive values 4, 1, 0, 1, 4 as shown here. And you'll get a graph as shown here. Let's say this is x-axis and this is the y-axis. Now you will find that it goes through the origin O, and the point here, which is a turning point, this is a very important part of the graph. We call this as vertex. It is a turning point. Now, in this particular case, the graph opens upwards. So these are a few characteristics which you have to look into. So let me list them. So we can see that this graph opens up. Now whenever it opens up, in that case will have vertex as minimum value, right? So in that case, vertex is a minimum value. I'll write vertex is a minimum. So we can say at origin we have minimum for this particular function. Correct? You also notice here that graph has a symmetry. Now the symmetry is along the y-axis. So it will always be symmetrical along a vertical axis. This symmetry is along y-axis, whose equation is x equals to 0. Correct? So this is also very critical. When we say symmetric, it really means that if I take a point on the left side of the graph, then there is a mirror image such that they have coordinates as, let's say, AB. In that case, coordinate of this point will be minus AB. Right? So what I'm trying to say here is that for the particular function, for any value, if x equals to a gives y equals to b, then x equals to minus a will result into y equals to b. The y values are same. Do you see that? For plus and minus x values, right? Now this type of a relation is also called, so what you also see is there are more than one values giving one value of y. So we call them many to one. To relation. Here you will notice that x value could be any real number. So we say x belongs to real numbers. Now in this particular case, since the y value is always greater than equal to 0, so we can see that y has restrictions. And in this case, y belongs to real numbers and is always greater than equal to 0. Now the characteristics which I am giving you are for this particular graph, which represents y equals to x squared. Now soon we will learn set notation, where we like to put these under curly brackets. Right? So set of all the real numbers, and we call x values as domain and y values as range. Right? So that is for our future classes. But I hope you understand few basic characteristics. Now let me give you some interesting ones. We found that the second difference is constant, right? So in this particular case, the a value is 1, right? So there we found that second difference. Let me write down delta 2y equals to constant. Correct? You will notice that the second difference in this particular case, if a equals to 1, then second difference, which I'm writing like this, will be 2. So there is a relation between the leading coefficient a. What I mean by a is something like this. We have the equation as y equals to ax squared plus bx plus c. So we're talking about this a, right? So this a is related with the second difference, and normally this a is equals to half of second difference. That is a relation. Okay, so in this particular case you will find that second difference, not the first one, second difference will be constant 2. First difference is not constant. You can see First difference is here we have 3, then we have minus 1, here we have 1, and here we have 3, correct? But if you find 3 minus 1, you get 2. 1 minus minus 1 is 2, minus 1, and then minus 1, minus 1, this is minus 3. Minus 1 minus 3 is also 2. So the second difference is constant, right? This is my first difference, which is not constant. Perfect. So actually, you should do it properly so that you understand. Second difference is 2, A is 1. Do you get this part? Correct? So that is very important. And in this, if it is opens up, we call this as concave up. So whenever it is concave up, we'll have absolute value of minimum. Correct? So these are very important things. Lastly, I would also like you to tell you that if we look into rate of change, that means if I draw a tangent line, then in this part it is negative and here it is positive. So what we also notice is that the slope at any point, which we call as rate of change, that rate of change increases all throughout. So another important point is rate of change. This slope, you can say, increases from left to right. So we write slope increases from left to right. So always increases, right? It is negative, 0, and positive. So it goes from high negative to 0 to high positive value. It is very steep here. Do you see that? So these are very important characteristics of a parabola to keep in mind. Okay, so let's move on and take some interesting questions based on this. We'll actually explore more the characteristics when we learn about different forms of quadratic equations. Now here is a very interesting question based on what we have just learned. If the second finite difference of y equals to ax squared plus bx plus c is 4 and the vertex is at 3, 0, then what is true about the graph of parabola? We are given 5 conditions. Maximum at x equals to 3, minimum value of 3, maximum value of 0, y-intercept at 3, minimum at x equals to 3. Right? You can pause the video, answer this question, then look into my suggestions. Now what does it mean? We are given vertex which is 3, 0. Now that gives you either a maximum or a minimum, right? So it could be either. So we can find whether the graph opens up or down, then we will decide. Now we are also given that second finite difference is 4. So second finite difference equals to 4. It means what? It means that in this equation of y equals to ax squared plus bx plus c, the value of a is half of 4. 4 divided by 2, which is 2. So important thing here is that a is greater than 0. It is positive, correct? So if a is positive, then parabola opens up, right? So we know since a is greater than 0, parabola opens upwards. You get the idea, right? So if you have a parabola which opens upwards, kind of like this, then what will the vertex represent? This is your vertex, correct? Which is at 3, 0. It is definitely the minimum. Perfect. So this represents a minimum value. So it's minimum. Now this minimum is at 3 and the value is 0, right? So minimum at x equals to 3 and minimum value is y equals to 0. So when we say minimum value, we mean the y coordinate. Now let's read it. The first one is maximum, not connected. Minimum value of 3. No, the minimum value is 0, not 3. Maximum, no. Y-intercept, this is x-intercept, not y-intercept. So since the y value is 0, it is x-intercept. So this one also is x-intercept, not y-intercept. Last one is minimum at x equals to 3. That is true. So option E is the right option. Does it make sense to you? This is a very important question. I hope you have understood the concept, right? Now here is another one from the same value. So we have similar question, exactly same. If the second finite difference of a equals to x squared plus bx plus c equals to 4 and the vertex is at 3, 0, then what is a? Well, we answered last time. A is equals to half of this, 4 divided by 2, which is 2, right? So option D is the right option. Perfect. Now these are two very important questions based on this particular chapter. Let's move on and take an application question based on quadratic relations. So here is a real life application. Path of a ball is given by the equation h equals to minus 5x squared plus 10x plus 15, where x is greater than or equal to 0. Where x is a horizontal distance in meters from a building and h is the height of the ball in meters above the ground. You need to answer these three parts. Find the height of the building from where the ball is thrown. What is the maximum height of the ball and at what horizontal distance it occurs? C. Sketch a graph to represent the path of the ball. Correct? So these are the three questions for you. You can pause the video, answer these questions, and then look into my suggestions. Now we should actually begin from part C, that is to sketch the graph. We know the equation, so what you should be doing is that, let me just take some x values and then we'll calculate the value of y. So if I take, now since x is greater than or equal to 0, so we should start with x equals to 0 itself and find height. All are in meters. So if I substitute 0, I get 15. Now, for the next value, I can substitute a value, let's say 1 for x. So if I write 1 here, what do I get? You can use calculator also, right? So that's not a bad idea. So if I write 1 here, then I get minus 5 plus 10 plus 15. So 25 minus 5 will give me 20, correct? Now let's substitute 2. So use calculator, I'll prefer that. So if you write 2 here, I have very less space, so I'm just putting them all together. So if I write 2 here, I get 2 squared as 4. 4, we get minus 20 here, right? And 2 gives me plus 20, and this is plus 15, correct? So I get value of 15 here. So now let's substitute 3. This I did for x equals to 2, right? Now let's calculate for x equals to 3. If I write x equals to 3, in that case 3 squared is 9. 9 times 5, we get minus 45, and 3 times 10 is 30, and we have a constant 15. So what we get here is 0. So that is to say that height is 0 means ball strikes the ground, correct? So we can now sketch this. So I've actually taken a very simple equation. The idea is to understand the concept. So what you notice here is that the ball is thrown, it goes up to a maximum height of 20, kind of like this, and then drops down like this, right? And what we notice that it starts now in this particular graph. Here we have height in meters and the distance x is in meters, correct? So this is the starting point. Ball is thrown from somewhere in the building, maybe the top, whose height from where it is thrown is 15. At 0 it is 15. Maximum occurs at x equals to 1, which is 20, right? So the maximum height is 20. At 2 it is again 15. Somewhere here it is 2. And at 3 it hits the ground. So this is at 3, it hits the ground. So the ball is in air for 3 meters. So that's the graph for you. Is it okay? Let's answer the questions. Find the height of the building from where the ball is thrown. Clearly it is 15 when distance is 0. So this is 15 meters. Second, what is the maximum height of the ball? 20 meters. Part B is at what horizontal distance it occurs? At x equals to 1 meters. And C, the graph is right before you. So I think with this, we got the basic concepts about quadratic relations. Now we will explore different forms of quadratic equations. So we could write, as you saw, equation in the form of ax squared plus bx plus c. We'll also write this in the form of x minus, let's say, x1 times x minus x2. And we'll also write this equation as, let me write y equals to, for each, a times x minus h whole square plus k. So these are 3 different forms which we are going to explore in the next unit. I hope that helps. Feel free to write your comments and share your views. If you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.